Welcome to the solutions for homework set number 5 for ECE 321 Analog Electronics. This homework looks at DC analysis of transistor amplifiers. So the first problem is, given this transistor amplifier, find the operating point. The trick is to take the Thevenin equivalent. So if we look at the base, looking left, what I see is a 300K to ground, 700K to 12 volts, 12 volts to ground. So here's the circuit equivalent. 300K, 700K, and 12 volts. Draw the Thevenin equivalent. So V Thevenin is by voltage division 3/10 of 12, 3.6 volts. R Thevenin is turn off the voltage source, and I get 700K in parallel with 300K, 210K. So there's R Thevenin, V Thevenin, or we call them RB and VB. Now we draw the circuit. From base to emitter, I've got a diode. So here's the base, here's the emitter. The emitter goes to ground through 2K. Emitter goes to collector through beta IB. Here's collector. Collector goes to 12 volts through 4K. So here's the same circuit. Now I can solve for IB. I know that IC is 200 IB. I know that IB, or VB, is equal to IB times RB plus 0.7 plus RE times IB plus 200 IB. Solving, I get IB is your VB minus 0.7 over RB plus RE times IB plus 200 IB, because that's IC is 200 IB. Gives you 4.7 microamps. Once I know IB, I know IC. IC is 947 milliamps. So now I can find the Q point, VCE, is 12 minus RC times IC minus RE times IB plus IC, 6.3 volts. So here's your Q point. Problem 2 is design. Design a circuit so that the Q point is 5 volts. And I stabilize the circuit for variations in beta. To stabilize the variations, I have this constraint. So 402K is much, much bigger than RB. Pick RB, say 10 times smaller. If VC is 5 volts, I know that VCE, back over here, VCE, if this is 5 volts, that's your 12 minus RC times IC minus RE times IC plus IB. Plugging it in, I can solve for IC. IC must be 1.16 milliamps. IB is IC over beta, 5.8 microamps. Once I know IB and IC, I can find VB. So it's IB times RB, and you got this circuit over here. Here's your diode. There's RE. It's this voltage, IB times RB, plus 0.7, plus IB plus IC times RE. 3.27 volts. So this is V Thevenin. R Thevenin was 40K. So I know that R1 in parallel with R2 is 40K. By voltage division, 3.2K. Solving, I get, basically pull this out. I can substitute. I get R1 is 12 volts over 3.2 volts times 40K. R1 is 146K. R2 makes the parallel combination 40K, 55K. So this circuit gives me 5 volts, collector to emitter, and stabilizes the Q point. Problem 3 says, now let's draw the small signal model for the circuit of problem 2. So if I go from the base, I see R2 goes to ground. Get that wrong. 55K. R2 goes to ground. R1 goes to power. Oh, AC analysis, this is equal to 0. This is actually 12 plus 0 sine omega t. We're doing AC analysis, so this is 0 volts AC. 146 goes to ground. Takes me to the base. Base goes to emitter through a diode. The diode is NVT over IB, assuming N is 1.45, 65, 25 ohms. 1.45 depends upon the diode. This is what Circuit Lab uses. Okay, it takes me to the emitter. The emitter is tied to ground through the capacitor. The emitter goes to collector through beta IB. and collector goes to ground through 4K. So here's the small signal model for that circuit. Now, find the two-port model. Input, I see these three in parallel, 5609 ohms. The input voltage is 0. There's no power supplies on the left side. Output resistance is 4K. Short the input, measure the resistance, so this goes away. I just see 4K. And the output gain, you got to work for. So let's make this 1 volt. The current is 1/6525 times 200 times 4,000. Gives you minus 122. So here's the two-port model. In Circuit Lab, I can check. I build the circuit in Circuit Lab. I make this like a 1 millivolt sine wave at the output. So the output impedance is large, basically infinity. I should see 122 millivolts, gain of 120. In Circuit Lab, I actually saw 144. So it gains a little bit higher than I expected. That's probably your N. So RF is NVT. Change N, I change the resistance, which changes the gain. Next. For Rn, define Rn, I'm going to change R8, make that bigger. What that should do is, again, think Thevenin equivalence. Here's the model for the two-port model. If I add a resistor right here, then this voltage drops by voltage division, meaning the output drops by voltage division. So trying that, to make Rn 5K, the output drops to 72 millivolts for a gain of 72. I can then calculate if this is 5K, what does Rn have to be because the voltage drop from 144 to 75. And that gives me Rn is 5020 ohms versus 5609 calculated. Define R out. Again, here's the two-port model for R out. If I add a load resistor over here, that's the same as R out, half. So let's try it. Put a 4K resistor at the output, and the gain drops to 73. From that, I can calculate what R out is. R out is 3817 ohms. So there's the experimental values, pretty close to what I calculated. The difference probably is this N. N is a constant for each diode. It's between 1 and 2. Circuit Lab uses 1.45 for 4004 diodes. For a transistor, we might use something just a hair less. Next problem. Add RE. Now find a key point. Correction. There's a capacitor right here. Get rid of that capacitor. Now, find the small signal model. So again, I go from the input. I see R2 to ground. I see R1 to ground. It takes me to the base. Base goes to emitter through RF. Emitter goes to ground through 2K. Emitter goes to collector through beta IB. That goes to the output through 4K. So there's your circuit equivalent. To find the input resistance, it's 146K in parallel with 55K in parallel with this mess. And this 2K, it looks like a 2K times 1 plus beta, because whatever this current is gets amplified, giving you that much more voltage from V equals IR. It looks like it's actually a 402K ohm resistor. So put these in parallel, and I get 21K. There's the input resistance. AI equals 0, apply 1 volt to the output, nothing happens at the input. The output gain, or R out, to make the input 0, IB is 0, beta IB is 0, all I see is 4K. To get the output gain, make this 1 volt. The current is then 1 volt divided by the total resistance, 6525 plus 402K. Gives me the current. Current times beta gives the current over here, IC, and I times R times 4000 gives the output. Gain is 1.95. In Circuit Lab, I can test that. Get rid of C4, or what I did is just make it 1 nanofarad, so small it basically has no impact. Now, do the same thing. Apply 1 millivolt here, measure the output, and I get 1.96 millivolts. Gain is 1.96 versus 1.95 calculated. Pretty close. Rn, I made R8 22K. I should get half. I got 1.15. From the previous calculation, so I can calculate Rn, 31K. Close, a little bit off. Rout, 3991 versus 4K. So with a circuit like this, I can experimentally find the two-port parameters. On the Rn, AI, Aout, well, AI is equal to 0, Aout, Rout. And that's kind of what the two-port model does. It predicts how the circuit will behave. If the two-port model is correct, it should predict correctly. And that's homework set number 5 for 321 Analog Electronics.